Okay, good morning, everyone. Any Peruvian football fans here? No? Any sad Australians? No? Where's Tracy? No, she doesn't care anyway. All right. Okay, so let's dig back in. Last time, we were talking about this critical item, right? The statistical model. If you had this, the probability of seeing some data in your experiment given some theoretical construct, if you had this, then you could do all sorts of cool stuff, right? This is the basic element you need in order to interpret your data, right? In order to make inference, which is what we want, because we're going to see some data, we want to make some statements about theta, right? So we want to be able to take this and eventually get to something like probability of theta given x if you're a Bayesian, or something similar if you're a frequentist. But we at least need to be able to start from this in order to get there, right? And so what we said yesterday was this is intractable, right? And I didn't mean to make it sound hopeless, right? I meant that as a call for good ideas and genius breakthroughs, right? Maybe someday one of you will be able to write down a function that describes this. As an aside, one of the things I love about theorists is how they have taken over certain words and given them special meaning. Like for a theorist, to write something down is like a moment of creation, right? Like I can write down a theory, like, and it's as if when you write it down, then it comes into existence in sort of like the theoretical mental space or something. Like you can't write down a theory that, you know, like, anyway, it's funny to me. So maybe someday someone will be able to write down this function, which is like a great moment in theoretical physics. Anyway, not today. And so we were talking yesterday about how to address this problem, right? And one classic, this is not the one that slides. Are there supposed to be three here? I only see two.
I think that one goes up. The bottom one goes up.
This one is also, oh, okay, yeah, there we go. That's the second one. Great. Okay, and so the classic approach, the sort of default approach, is to model with Monte Carlo, right? Since we do have an excellent understanding of the microphysics, the little pieces that go into what happens when you have a collision hits the detector, we can at least generate simulated examples, right? Can generate arbitrary numbers of examples from which we can recover some approximation of this statistical model in low dimensions, right? So we can model it with Monte Carlo, and you have, for example, some distribution of your data, right? And you can make some model with simulation to attempt to describe that. This is one dimension, right? Okay. Now, the reason we don't just stop there is, the reason this is more complicated is that the Monte Carlo doesn't always work, right? The Monte Carlo is an approximation. How is it an approximation? Well, even the part that we do understand well, mad graph, is not to all orders, right? We have LO or maybe sometimes NLO calculations of the hard scattering. So we're definitely ignoring some critical elements, right? The other pieces of it, Pythia, is definitely an approximation. I mean, it's essentially just a heuristic, right? Nobody believes that nature follows Pythia, that if you tore open the recipe book of the universe, you would find, Fortran code in there with 500,000 parameters, right? But it works, right? So it's effective, right? And so it's definitely an approximation. And then, of course, Géant is a similar tool. It's at least rooted in actual physics, things that we understand, experiments we've done to calibrate this.
So Pythia is C and it gives you these strings. So it's not as bad.
Okay, right. Yeah, you're right. It's likely that the universe runs on C. I agree with you, Tillman, yeah. It's, import universe, right? Yeah. And then Geant, of course, is excellent. It's grounded in real physics, but of course it's approximation, right? It only models things down to a certain energy level. There's lots of approximations here. So we don't expect this to be perfect, right? Nobody would ever expect this to be perfect. And in addition, there's things that are just difficult to model. You know, lots of fluctuations, things that are hard to model. Fake leptons, etc. And you know, Geant relies on a description of the detector, which is a description of an idea of the detector. It's not the actual detector, right? And so it's going to be a little different. It doesn't have necessarily all the details of it. We assume things are homogeneous when they're not. We assume things work when they don't. And so there are going to be approximations here. How do you handle that? How do you describe the uncertainty in your model, right?
So this might be as cool as going, but I've never heard the term fake lepton before.
Okay. What is a fake lepton? A fake lepton is an object in your detector that you think is a lepton, but is not. So for example, a stream of hadrons could decay primarily to a pi zero, which turns into 2 photons, which you might reconstruct as an electron in your detector if you find it an electromagnetic cluster with a track. You think it's an electron, wasn't an electron. Or a jet could punch through and hit the muon chambers, and you think it's a muon, it was actually just a jet. These things can be difficult to model because they are low probability events. Great, thanks for the question. Okay, so how do you handle these things? Well, there's good ways to handle them, there's bad ways to handle them, there's worse ways to handle them, and then there's wrong ways to handle them. Okay, and we'll talk about some examples of each one. Let's talk about a good example. Okay. Right. Let's talk about just uncertainties in your model. Say, for example, you are using some model like Pythia, and it has a parameter in it. Some parameter that controls how much gluon radiation there is. Right? Guys writing this thing said, well, we could have more or less gluons. We don't really know. It's an unknown, so we'll just put some parameter in there. Okay, and we'll write it down as nu. Nu being short for nuisance parameter, as in a parameter we don't care about very much, but we need to have a value for. And you know, you have, for example, some process that looks like this. You know, maybe you have a Z that goes to 2 leptons, very nice clean process. And here you can have gluon radiation, right? How much gluon how many gluons get radiated at various PT? You might be able to do that with a strict QCD calculation. Pythia just has some model and has a parameter in it. It's either more or less. Okay, and this is really the way it works. In fact, there's like 7 parameters you all need to tune. So what do? How do you know what value to put for this parameter? You put in different values for the parameter, you get different predictions, right? So you want a prediction that describes the data. What do? Well, what you can do is, for example, look at the data here and say, I'm going to collect events with 2 leptons in them, see that this is Z, and then I'm going to look at the observed number of jets, right? And so maybe my observed number of jets, you know, it should fall because the probability of an additional jet is smaller. And then what you could do is you could say, I'm going to plot Pythia's predictions for various values, right? Like maybe this is Pythia's prediction for some value, nu0, and then if you tweak the knob, you get more gluons, right? And so you get something like fewer with 0 and, you know, I don't know, something like this, right? So they call this nu1. And you could also tweak it the other way and get another prediction with fewer gluons, right? Something like this. All right, so you have 3 values here. You have some nominal guess, and you have, this one is more, and this one is less. Okay, this is a good situation. Why is it a good situation? Well, because you have some data that can tell you what value of the parameter you need, right? You can say, well, the data tells me that nu0 is the best description, right? And so this is good because you can tune the parameter to the data. Right? And also, you can extract some uncertainties. Right? You can say, well, the best value is nu 0, but we have some statistical uncertainty because our data set's not infinite. And so it's also consistent, at 1 sigma with this value or with that value. You can get essentially a likelihood of various parameters, right? And this is excellent because it means that it scales with your luminosity, right? You run the collider another year, you get another, you double your data. These error bars go down. You can make a more precise statement of nu 0. As you run your collider for another 5 or 10 years, you can really nail this parameter down and say, this value of the nuisance parameter gives me my best description of gluon radiation in Pythia, right? And that's critical because you're not only interested in this process, zeta leptons, gluon radiation is going to affect all sorts of things. You want to make a very precise measurement of the top quark mass, right? Your model needs to have an accurate estimate of the number of gluons that are radiated, because those are going to screw up your measurement if you think those gluons came from the top quark, right? Both in this case. We're always doing a histogram, so you're always going to have a step function, and this does happen to be an integer. Although there's a really cool paper by Jesse Thaler a couple of years ago about non-integer jets, which I thought was a cool idea, but it doesn't really have any useful applications yet. Okay, so this is an example of a good situation. You have a parameter, you don't know what to do with it, but you can constrain it in the data. And these values make some sense, right? You can get a sense from these uncertainties, like what's 1 sigma up or 1 sigma down in terms of this parameter, okay? All right, so we'll call this the good, right? These are good uncertainties, right? All right. Here's a one that's less good, right? Say, for example, in a similar setup, you want to know what is the PT distribution of your Higgs bosons, okay? Right? You have Higgs produced in this way, and then it decays in some way. I don't know, maybe you're looking for BB bars, right? So this is gluons, fermion, fermion, fermion. And you want to know what's the PT of the Higgs boson, because maybe there's, again, additional radiation here, or from the B quark. What's the PT distribution of the Higgs boson? Okay, because if the Higgs is boosted, it means the B's are going to be closer together, and if it's not boosted, they're going to be back to back. And so you want your Monte Carlo to predict this correctly, right? And typically, this is a difficult thing because calculating all these gluons, especially a large number of low PT gluons, can be difficult. Even calculating a large number of high PT gluons is difficult because then you have lots of diagrams to calculate, and there's loops in here, et cetera. And so what can be done sometimes is you say, here's my data, right? Here's my model, right, which almost always underpredicts the PT distribution. Now, maybe you don't have a good parameter, right? Maybe there's not an easy knob to tune to get this thing to match the data like there was in this case, right? And so what sometimes people do is they say, well, I'm just going to reweight my events. Okay, I'll take, I have bins here, right? And I can say, in each bin, I can say, okay, for Higgs PT between 40 and 60 or whatever, my Monte Carlo model underpredicts by 20%. So every event in this bin, I will reweight and give it a 1.2 weight. And here, maybe it overpredicts, and so I'm going to de-weight it. And that will, by construction, give you a PT spectrum which matches the data, right? Okay, so this is somewhat one way that you can handle having data Monte Carlo discrepancy. Problem with this is that it's It's a 1D fix, right? It fixes this distribution. It doesn't give you a complete model that makes predictions which you agree with and understand, right? It fixes this distribution. It might break another distribution, right? Who knows if it even solves your problem? It gives you no insight into what's going on. It doesn't improve the quality of your model. And it doesn't give you any uncertainties. It doesn't scale well with Monte Carlo, right? It doesn't improve the situation at higher Monte Carlo. Sometimes it's all you can do, right? If you don't have a nice parameter in your model that you can tweak to get this right, then it's all you can do. But it's not a great situation. And it's hard to know also what the uncertainties are. Like you can take some uncertainties from these, from here, but you don't have, again, a parameter in your model that you're really constraining. And what do you do for, this might work for this analysis, right? What do you do for another Higgs analysis? Can you take the same weights and apply them somewhere else? You learned something very specific. Maybe you solved your problem. It's more like a Band-Aid than really describing an uncertainty, okay? And so this, I would say, is a bad uncertainty, right? And it gets worse from there, right? Maybe you're doing your analysis and you have some prediction of, let's use the PT distribution again. You have a prediction from Pythia, right, of your Higgs PT. But your buddy is from the UK and he says, I don't like Pythia, I prefer Herwig, okay? Herwig looks like this, right? And it's written in C++, so there, okay? Herwig looks like that. And then your data is like, somewhere close to both of them, okay? So now what do you have? What you have is a model that uses Pythia, and you have a model that uses Herwig, right? What can you do? Well, you can't handle it the way you handled this, where you have a parameter that varies, right? You can't smoothly vary between Pythia and Herwig, right? Like I'd like 40% Herwig and 60% Pythia, right? There's no sense in that space. You can't. You make this choice or you make this choice, right? And inside each of these models, you have nuisance parameters that let you tweak it, but assume you've already done as much tweaking as you can. People are really unnerved by this. They say, well, I don't like making an arbitrary choice of Pythia. There's this other choice out there that gives me another answer that feels like there must be something wrong with my measurement. And so what people typically do is they say, well, I don't know what you're measuring. Say you're making a measurement of the Higgs mass, right? What they will do is they say, well, here's my Higgs mass measurement if I use Pythia, and here's my Higgs mass measurement if I use Herwig, okay? So what I will do is I will take this difference and call that a systematic uncertainty, right? This is the, I don't know what I'm doing, cover my ass uncertainty, right? Okay, what's wrong with that? Well, so many things. First of all, what if somebody comes along and invents another one, right? Okay, so now you have Pythia and Herwig and, here's Sherpa. Okay, well, they're definitely not going to agree, right? So now you're going to take the envelope of all of them as your systematic uncertainty. See the problem with this as the number of Monte Carlo generators grows, right? As people generate their new systems.
So, because it makes me feel like there's something really weird happening in the code. It's one of the fundamental things when you have codes you want to verify if they're getting the right thing, but being able to reproduce it. If these codes are just giving you different answers, doesn't that mean that there's something fundamentally in the physics that they're being prevented to happen?
Neither of them are fundamental physics. They're both black boxes that have, some approximation, some reasonably well-motivated bits inside, but neither of them are fundamental descriptions of anything.
So how do we know any of them are correct?
None of them are correct.
I disagree a little bit. All of them do. All of these codes are based on their fundamental physics concepts. But there are parameters. Any fundamental physics concept has parameters under the equation, right? Or like you do it and those parameters need to be included somehow.
That's right.
Parameters are expected from data.
Yeah.
It can't be perfect. It can never be perfect.
Can never be perfect. And in a philosophical sense, is it correct? I mean, I don't even know if that has any meaning, but
But actually, I can
that should be on the T-shirt. Tazi 20. Nothing we do is correct.
from QCD perspective, Herbig and Sherpa, like I'm not looking at lots of talk, but exactly what Daniel is describing is what people do from part of this.
Yeah, no, that's on my list.
First, because there is a part of validity that everybody knows is nonsense. It is always included in the envelope because the authors push very hard to include the envelope, otherwise they cry. They will put their name in the envelope, and the uncertainty has nothing to do, I mean, like, it's wrong. It's really wrong because there's an envelope that includes something that's an outlier that the authors push into that thing politically, and the answer is simply a wrong L1.
That's right.
So, like,
That's right.
this is, I support this.
Yeah, and I mean, there are other issues there, like, say Pythia and Herwig, say you imagine there's some larger space of theories, of models, right? I don't know. And Pythia and Herwig sit here. Okay, but are they 1 sigma away from each other in this space? So you can take the difference and say, that's my uncertainty? What if they're 10 sigma away from each other? What if they're half a sigma away from each other? It doesn't even mean anything, right? A similar problem comes, and so the point here is you can't compare across models, right? These models don't live in the same space, you can't compare across them. Pick one, define the uncertainties in a reasonable way using the data and the parameters that you're given. The best model will have a small number of parameters and yet still be able to describe the data, right? That's the best model. But don't compare across them. And even there are problems inside models, right? Say, for example, so that's worse, right? Here's and then it gets even worse, right? Here's a wrong example, right? In my opinion. Sometimes there's a parameter inside a model that makes theorists uncomfortable, right? Like factorization scale or renormalization scale, where they go, I just don't know what to put, but it affects the predictions, right? If this is twice the number or half the number, I get different answers. So what do we do? And so then the theorists say, well, pick some number, I don't know, mz, and then also pick 2 other numbers, mz over 2 and 2mz, right? Why these numbers? Because we like factors of 2, right? Are these numbers 1 sigma away from this? In no reasonable sense are they 1 sigma away from this, right? Is this thing like, in this case here, you can imagine having a peak value and some uncertainties that might be Gaussian, right? That can feed in later to a statistical model. Here, you're just making arbitrary choices. Somebody else could have said, I think 3 is a deep number in the universe. I mean, we have 3 flavors of leptons. There's 3 elements of the Trinity. These arguments are as strong, okay? They're absurd. They're nonsensical, but they're as good as what we actually do. Tracy? Right.
I think there is a place for these.
Oh, yes.
Incorporated into your model as 1 sigma.
Yes.
But displayed as a band where you say, this is how sensitive our result is to the variation.
Yes, absolutely.
I think there is a place for
Yes.
it. You just have to be careful not
Right. So the right answer is not to ignore it and say, well, we don't know how to treat it correctly, so we'll just pick one number and pretend the problem doesn't exist, right? That would be even worse, right? The mistake is assuming that we can treat these uncertainties the way we treat well understood uncertainties, right? And then push them forward through some machinery that makes all sorts of assumptions about them. We need to remember that these uncertainties fall into categories. The wrong way to do it might also be the best way we currently know how, right? And as long as we have conventions and we all understand, look, what we're saying here is we don't know what to do, and we just want to understand, is this a big deal or a little deal for your analysis, right? If you change this by a factor of 2 and it has an enormous impact on your result, then hold up because there's something going on. If it has no impact, then it tells us something. But it's more of a sense of scale.
In that kind of scenario, is there is that also wrong?
It's very dangerous, right? Because it's a high-dimensional space. And if you're just picking a particular slice of other parameters to minimize your dependence in one parameter, your overall uncertainty could be getting larger, right? So thank you for that question. That leads directly into the next point, which is how people combine these things and treat them together. So let me say a couple words about that. All right.
I mean, just one comment while you're Whiteson, right? I mean, there is a fundamental Whiteson thing, right? I mean, it's not like another program.
Yeah, sure. We don't know what the right thing is to use, right?
It's a permanent artifact, and you know that like in all of this there is no scale independence, so it is at some level but of course, yeah. That's not what I don't even care which is the problem.
But the answer does.
Has no sigma. There is no sigma.
Exactly. Okay, so what do people typically do, right? You're using some model. Somebody gives you, your theory friend says, here's my Monte Carlo description of the backgrounds of the LHC, and I have some model, and I have some nuisance parameters, right? So these are nuisance parameters, right? And so what people typically do is they do something not very clever called the shift method. All right? What we'd really like to know is what is the dependence on your expected observed data as a function of these nuisance parameters, right? Like, as you change these nuisance parameters, how does your prediction change for what you should see at Atlas, right? Are you going to see more gluons, less gluons? This thing exists, right? The problem is, remember, we don't know what the function is, so we can't take derivatives, right? All we can do is sample. So typically what you do is you say, well, all right, I have my nuisance parameter. I'll use some nominal value. I'll use a value I'll hope is +1 sigma, and a value I hope is -1 sigma, right? Where this comes from depends a lot on the nature of the parameter. Is it determined from some other experiment in data? That would be great. Is it chosen for aesthetic reasons? Is it totally nonsense because it's Pythia versus Herwig, right? But you have several values, and then this is your expected measurement. Maybe you're measuring, again, the Higgs mass, right? And what you do is you measure it here, here, and here, and then you just look at this slope. And so it's called the shift method because you shift the value of the parameters. And typically, this is an enormous process because you have to generate millions of samples here and millions of samples here and millions of samples here. So you can't generate 10 different samples to understand the dependence here. And you make lots of assumptions, right? You assume it's linear, right? You hope that it's not doing this, or something crazy, right? You only sample from -1 sigma to +1 sigma, and you assume that it's linear, okay? In addition, you typically have more than one of these parameters, right? You have something for the radiation, you have something else for the factorization scale, something else for the normalization scale, right? You assume that these things are uncorrelated, right? And there's two ways these things can be correlated. There can be correlations in the underlying physics, right? Maybe somebody says, oh, if you have more radiation, that suggests this parameter should be this instead of that, right? These in the underlying physics. This is a solvable problem. You can think about your model and try to take these pieces apart and make sure they're independently capturing different uncertainties in the core physics. That's a solvable problem and is usually reasonably well done. For example, in parton density functions, they've tried to separate out the various sources of uncertainty into orthogonal directions, right? But then there's also the impact. Okay? We make this measurement, we say, all right, the impact Sorry. This is my delta M Higgs here. This is the dependence of this. This is assuming that all my other nuisance parameters are at their nominal value. Because when I run my Monte Carlo, I change this one parameter, but I keep all my other parameters, of which I might have 40, at their nominal values, right? You can imagine some larger space, nu 0, nu 1. These are two different nuisance parameters, right? Here's my nominal point for all of them. And what I do is I measure up 1 and minus 1 in this parameter, and then I measure up 1 and minus 1 in this parameter, right? But I always keep everything else nominal. What's happening here? What's happening here, right? I'm assuming that this is a simple Gaussian sum of this effect and this effect. But what if it's not, right? What if when this thing is plus 1 sigma, it changes the way this thing behaves? We've never studied that at all. Why? Because then you'd have to generate more than 3 samples for every uncertainty. The number of samples would have to grow enormously. And so it's just impractical because we can't generate that many samples for every nuisance parameter, plus 1 in this one, minus 1 in this one, right? We can't sample that at all, so we just pretend that problem doesn't even exist, okay, and assume that these things are totally uncorrelated.
Presumably your X isn't a single data measurement type thing. It's not just the value of one thing. You've got a lot of data about a bunch of different things in your model. Do you run these for each particular kind of data's piece for every nuisance parameter?
Well, typically you do it for the quantity you're going to quote in the end. So if you're measuring the Higgs mass, you really just care if it affects the Higgs mass. If it has some other complicated effect on some internal intermediate number, that's interesting. But really you care, does it affect the quantity you're going to make statements about statistically, right? You want to write a paper that says Higgs mass is 125 plus or minus X. And you want X to be small. You want X to be well understood, right?
You have like multiple observables that you're doing at the same time?
Yeah, and sometimes you can have multiple observables, Higgs mass and cross-section. And then you can do ellipses in that space. Yeah, there's no limit on the dimensionality of that. It gets harder and harder as the dimensionality gets larger. Okay, so we use this shift method. It's very low tech. It's sort of the best that we can do. Okay? Also, sometimes you have problems. Like, what do you do if you do the shift method, right? And so here's 0, plus 1 sigma, minus 1 sigma. Here's your observable, maybe mass of the Higgs. Here's your nominal point. You do the plus 1, it's here. You do the minus 1, it's here. Like, uh-oh, now what do you do, right? You don't know what this function looks like. So typically what people do is they say, well, I'm going to take the deviation from 0, the maximal deviation from 0, and quote that. But again, like, we really just don't know what we're doing. We're taking 3 samples here from the function we have no understanding of. And even when this is small, right? Like, if these are small, are they small out beyond 1 sigma, right? It could be that this thing is huge and then has a plateau and then it gets large again, right? So we get these individual numbers that say, here's what it looks like at plus 1 sigma and minus 1 sigma, right? And then we fold those into our statistical model and we treat them like they are well understood. And we push that forward into our machinery later, whether or not it makes any sense at all. Okay?
If you happen to sample out further than plus or minus 1 sigma, and found something that looked like that, what would you make of that? What would you do in that case?
Well, you would try to do something smarter than just linear. You try to do some piecewise linear thing or find a function which fit it, right? So, because the thing is, why do you need to know? Well, you're going to need to know values other than 0 and 1 and 2, right? You're going to need to know, well, 0.5 or minus 0.5, right? Because later on we're going to talk about this in a moment, you're going to be sampling over this space, right, and saying, well, this is the most likely value, this happens sometimes, this happens sometimes. You're going to be sampling over this space, so you need to know the dependence on intermediate values. So you need some way to describe that, right?
Can you put in a test where, like, for maybe just one of these parameters would be significantly more than confidence, and you sample the space before you just confirm that it's doing what you think it's doing, something like that. Just 1 or 2 in a test case.
Yeah, that would be great. But, we're always in a hurry. There's always some conference deadline approaching, and we've done things a certain way. And so the suggestion of, let's blow this up and do it 10 times more complicated just to make sure, never goes over very well. I mean, if you're going to redesign this from scratch and you had infinite resources, you would totally do it differently, right? But this is sort of the state of the art. It wouldn't be complicated. It would just be expensive from time and, and computing resources, which are always limited, right? Related to your question, we measure it at 0 and -1 and +1, right? Sometimes we need to know it at a half, right? What does it look like at a half? Well, we don't generate simulated events for every case. What we do is we interpolate, right? Say, for example, this is your Higgs mass, right? And you have a histogram for what happens for your nominal value, right? μ0. And then for your shifted value, you have another histogram, like this maybe. And then you have for your, that's μ1. And then for your other histogram, your other shift, you have the other direction. All right, this is μ2. How do you, so this should be μ +1 and μ -1, how about that? -1 and +1. How do you get μ at a half? Well, you interpolate, right? You say, I'm going to assume that μ at a half can be interpolated bin by bin, right? There's actually 2 ways to do this interpolation. There's what we call vertical interpolation, where you literally, in each bin, you say, well, if this is 0 and this is -1, half is going to be halfway there, right? It's no more clever than that. And you can do it piece by piece. Vertical interpolation works okay, right? But you can very easily think of examples when it would totally fail, right? If you have like a Gaussian here and a Gaussian here, and you're trying to do vertical interpolation between here and here, it's just not going to work, right? You're going to destroy the shapes. So there's another approach which is called horizontal interpolation, right? And that takes the cumulative distribution function, the CDF of these histograms, and interpolates that instead. And that does a much better job at doing this kind of interpolation, but not as good when they're close together. So sometimes we do vertical, sometimes we do horizontal. But what we never do a good job of is extrapolating, right? You want to know what does it look like at 1.5 or at 2. You're just going to assume that there's a linear dependence here and extrapolate off into crazy land. It's very delicate, okay? All right, so let's keep going so we can get to the fun stuff. There are other ways to build statistical models other than just saying, I'm going to take a Monte Carlo simulator and try to tweak its parameters until I get it something close to right. All right, there are other approaches. Right, and some of them are much simpler, but they have their own weaknesses. All right, so how else can you build a statistical model? Well, you can do an effective model. Right? In some special cases. Say, for example, you are looking for a resonance, right? In, I don't know, the mass of 2 jets. Okay, and you have, you know from simple physics arguments that the background should look like this, and the signal should sit on top of it and be fairly narrow, right? Here's your signal, here's your background. Okay, and you can even write down an analytical function that describes your signal. Maybe it's a crystal ball or even a Gaussian or something. And your background is fairly smooth, so you can fit it to some parametric function, right? So here, you can just use parametric functions of your last x, right? You start with 100 million pieces of information, you boil it all down, you reconstruct your jets, you find a pair of jets, you calculate their mass, you have one piece of information now for every collision. You have your histogram, your spectrum of this, right? And you look at your data, and you have a lot of background only regions, right? Your signal is fairly narrow. It's constrained to a region, so you can have a region here to test your background model and a region here to test your background model to establish what are the best values of the parameters of your function, right? To interpolate, essentially, under your signal peak, right? This works very, very well in a simple case. You don't care you don't need a complicated model of your detector at all, right? You don't need to know how many gluons are being rated, what is the factorization scale. None of that is relevant if you have a fairly simple setup, right? If you're doing something more complicated where your background is a crazy shape and there's no function that can fit it, or your background and signal occupy the same region and you don't have these side bands where you can constrain it. But a lot of discoveries were made without detailed simulations, right? Because you can just do a simple effective model. And you can even get uncertainties on these models, right? Now, the downside is that it's fairly ad hoc, right? What is the function that you're going to use to describe this background? Do you have a good physics argument for it? Well, in particle physics for this one, MJJ, there was a paper from UA2, and I think it was 1984, I have to look it up, where somebody found a function that worked pretty well. We've been using that function ever since, right? Why? Because it's in the UA2 paper, and then CDF used it, and then Atlas started using it, and then it started to not work very well because we got lots more data, and a parametric function is never going to be able to fit a very high multiplicity sample, right? When this starts to get to be like 10 to the 7 events at low mass, your function is never going to predict it very well, and even a small deviation is going to cause a terrible chi-squared, a terrible goodness of fit. If you have, 1,000 points, you're 1,000 or 1,000,000 points off here, right? Even at 1% or something. So you just keep adding complexities, right? So they wrote down some function, I don't remember what it is, and we just keep adding terms and making it more and more complex to make that function more and more flexible, and so that it fits. And I can tell you, because I work on this analysis at Atlas, currently we do not have a function which describes the entire spectrum, right? From below 1 TeV up to 5-ish TeV, there's no function which describes it well. So what do? Well, we're working on some cool approaches. I can send you a paper about it. But what we're actually doing while we work that out is we just take little windows. We say, well, we can describe this section of the spectrum using our parametric function, so that's okay. We're going to describe this section of the spectrum. It doesn't work great, but it works reasonably well. It's a solid physics argument. You can make a reasonable physics argument that the background should be smooth, right? Yes, you need a different parametric function for a different situation. Absolutely. Just fitting the background to some function, yeah. And then you get into murky territory like, you would get a different result if you used a different function, right? Is that a source of uncertainty, right? It's tricky because you can induce biases by choosing different functions. On the other hand, there's an infinite number of functions you can choose. So in principle, that uncertainty can grow to infinity. So we try to do some clever tests there to think about the complexity of the function that's needed. But it's all very ad hoc and hand-wavy. Is there another question?
What did you mean by last step?
I just mean the final quantity in your analysis. Your data, your most reduced data. So, like MJJ. But this often works, and it's lots of glorious history of discoveries, right? So that works as well. Are there other questions about that? Okay. A similar approach is a data-driven model. Okay. Or here you say, I don't have some function that describes my spectrum. But I can construct one from the data, right? I can extrapolate from some control region, right? So let's think of an example. What if you are looking for some dark photon that gives you dark matter at the LHC, right? So this is QQ goes to dark matter, right? You can't see this, obviously, because it's totally invisible. And so we typically do it at collider as we say, let's assume we've radiated off some high PT gluon that turns into a jet. This is the classic monojet analysis. And what you look for there is a jet with nothing on the other side. And so your signal is, looks like missing transverse energy, the imbalance of momentum in your analysis, right? And you expect it to look something like this. Problem is that you also have backgrounds, right? Backgrounds like Z goes to neutrinos, right? Which can also radiate a gluon and looks just like your signal. And so maybe your background is like this, and your signal is essentially just an enhancement on top of the background spectrum. So it's difficult, you can't just fit this, your signal is everywhere, right? You can't say, oh, my signal's localized so I can normalize my backgrounds here and then extrapolate. Your signal is everywhere. And you don't really understand your background very well. Like it's difficult to get a really firm theoretical prediction for high PT Zs because it involves gluon radiation, which is, of course, difficult to calculate very precisely and is affected by things like factorization scale, which nobody wants our results to be very sensitive to. So what can you do in this case? Well, in this case, what you can do is extrapolate from some region where you think you can measure your background, right? So if the issue is that you have these Zs that are radiating gluons, you could say, well, what happens if my Z goes to 2 leptons? L plus L minus, right? You don't expect to see any signal there. So now you have you can look at your spectrum in missing ET, and you have only background, right? So this is your L plus L minus, and this is your nu, right? You can say, well, I can look at this spectrum, missing ET in the case when 2 leptons and a jet, right? And I can ask, what does this spectrum look like? And because the missing ET is generated from this gluon, which should be the same if the Z goes to neutrinos or goes to leptons, it shouldn't be affected, I can essentially measure the shape of this spectrum here. And more than just measure the shape of it, I know how often the Z goes to neutrinos versus goes to leptons. That's very, very well understood. So I can just take this spectrum and put it here, multiply this by the branching ratio of Z to neutrinos divided by the branching ratio of Z to leptons, and boom, I have a model for my background. I even have uncertainties on it because I have statistical uncertainties here. I have uncertainties on this extrapolation factor, right? And it's to all orders, right? There's no leading order calculations here. Nature does its calculations to all orders in 0 time, right? For those of you interested in the philosophical question about are we living in a simulation, I've always wondered about that. Like, you can use the universe essentially as an infinitely fast computer, right? Sometimes I think of like, that's what experimental physics is. It's really just like, setting up the universe to be an infinite speed computer. Anyway, so the universe generates this background for us, and we can just extrapolate it over here, and we say, this is a solid description of the background. So this is a very powerful approach. There are some limitations here. You have to find a data sample like this. You have to come up with some sort of experimental cleverness to extrapolate from one to the other. But this is a very powerful approach. Questions about that? I know they cannot see the neutrinos.
So why is the transverse momentum in the gluon, not the neutrino?
Well, the reason you have missing transverse momentum is because you can't see these. The sum of this and this and this will add up to 0 momentum.
And I don't think I understand the analogy to where's the missing transverse momentum in the lepton case?
Okay, great. So you take events with leptons in them and you delete the leptons. Yeah.
Okay.
Right. You say, let's say I didn't see them. What would that be? Or equivalent, you could say, what's the PT of the lepton pairs, essentially. Okay. One final approach is an attempt to sort of get back to the theoretical underpinnings. Okay, and actually do that intractable integral. All right, so remember, we said P of x given theta is an integral over dz of the probability of z given theta times the probability of x given z. Is that right? Yeah. So this would be, for example, so call x your observables like we usually do. Z are, for example, parton level quantities, unobserved, right? And theta are our theory parameters like usual. Okay, so then what is this piece here? This piece are just the matrix elements squareds, right? Including the PDFs and all that kind of stuff. This says, what's the probability for your given theory to generate various parton level form momenta, right? And this part is pretty well understood, right? We have computer programs that can generate code for us for an arbitrary process to calculate this, at least at some orders. This piece here, right, this says the probability of observing something in your data given parton level four vectors. This is the tricky bit, because you need to know, given some set of muons and quarks, what jets are you going to see, what's the probability of measuring various muon momenta. This is all the tricky bit, okay? This is why we can't do this integral, because we don't know how to write that down. So let's instead assume that we can write it down. Or let's write down a simplified version of it, because instead of throwing up our hands and saying, totally impossible because we can't do it exactly correctly, how well can we do? Okay? It depends a little bit on the nuances, but this shouldn't depend on theta. Like, doesn't matter what SUSY scale you're thinking about. Does your muon reconstruction efficiency depend on the SUSY scale? Probably not. A muon is a muon is a muon, and the same thing for most particles. However, if your theory has new particles in it that are long-lived or decay weirdly in your detector, then it could. So for full generality, you might put theta in here. For most cases, you don't need to. Okay, so we can say, well, what if px given z is pretty straightforward? Okay, what if we say that it's for muons, it's a delta function, right? Muons we measure perfectly. Okay, that's not true, but it's not far from true. We do a pretty good job of measuring muon momentum, right? In fact, what if we say that for all leptons, we measure them perfectly, right? And then for jets, we have some function, we call it a transfer function, for x and z, right? So we have jets, we have leptons, we don't see neutrinos, right? So neutrinos are just, there's no information there. But what if we just wrote this down and we said we assume a one-to-one connection between partons and observed objects, right? Every quark gives you exactly one jet, right? And we can even break this down and say this guy is going to be a delta function in angles, right? We'll assume that all our jet angles are well measured, because that's also, we do a pretty good job there. And that only in jet PT do we need to PT jet versus PT parton. All right? This is suggesting most of the tricky bit is inside the jets. And what if we had some function which related the measured PT of jets to the true PT of partons? If we had a probability distribution for that, right, that is the probability of measuring various jet PT given a parton PT, then we could do some approximation of this integral, right? Because we've simplified most of it. Now, this includes a lot of assumptions, right? What are we assuming? Let's be clear. We assume that leptons are perfect. I do like leptons, but they're not really perfect. Okay. We assume that jet to partons are one-to-one, right? Every jet leads to a parton. Every parton leads to exactly one jet, which we know is definitely not true. That jet angles are perfect. right? And that jet PT can be described, right? And that's not too bad, because this part here, the thing that tells us the probability of measuring a certain jet PT given a parton value, we can figure that out using our simulation. When we say, okay, show me the distribution, we run our simulation, we push it through Pythia and Jant and all that stuff, we get a description, we can write down a parametric function that describes this pretty well, and then we can actually do this integral. Okay, so this approach, just a moment, it's called the matrix element method. What do I mean by they're perfect? I mean that the parton quantity and the observed quantity are the same. That we have infinite resolution to see these things. Okay, so this is called the matrix element method. People still argue about who invented it and when, but it came into wide use at D0 in the early 2000s for measuring the mass of the top quark. And it was a very powerful method because it lets you calculate directly the probability of seeing various things in your data. And so then for an individual event, for one event, okay, you can take this P of x given theta, you can turn it around to get P of theta given x, as using some Bayesian stuff we'll talk about in a moment. And for an individual event, for example, for the top quark mass, you can get a probability distribution for what is the top quark mass given this one event, right? And different events will give you different shapes, like, right? Some events might have two peaks. They say, well, you can interpret this event this way, like, well, this jet goes to this parton, or this other way, this jet might go to this parton. And they also tell you something about how well measured they are, right? We have here something that tells us the probability of measuring various partons of various jets. If we do this cleverly, like we know which jets are well measured, like high PT jets have a better energy resolution than low PT jets, then we have some constraint on what's actually going on. We can say, this event was a really well measured event. This event tells us a lot about the top quark mass. This other event, really sloppy, not much information there. So maybe it, goes like this. So every event can contribute different amounts of information, right? That's huge, right? That's huge because in our previous approach, here for example, classic study for a mass, you have every event gives you one piece of information, and that's just what is the most likely reconstructed mass value, right? It doesn't tell you anything about whether other values were almost as likely, or whether that one is really telling you, hey, listen to me, I know what the mass of this thing is, right? So this is really powerful because it lets you do essentially per event in Monte Carlo integration. You say, okay, I saw this event, tell me all the configurations that could have given me this event and which ones are more likely. So instead of doing a whole bunch of super generic Monte Carlo generation to describe the whole spectrum, you're saying, here's the data I saw, do all the integrations for me to figure out what the various probabilities of various parameters were. So very powerful method, very cool. The disadvantages of this method are, of course, it's an approximation. I mean, we're making all these approximations, right? And even after you make all these approximations, you still have to do this integral. This integral can be 6-dimensional, 8-dimensional, 10-dimensional, depending on the complexity of your final state, right? If you have 8 objects in your final state, you're going to have a lot of integrals to do. And so you're talking about doing high-dimensional Monte Carlo integration for every single event that you observe, right? Over here, we might have 10 million events that we observe. You can do this massive calculation for every single event. It takes a lot of time. So it's very slow. Although recently, there's some very nice breakthroughs in machine learning that might make this much, much faster. Maybe we can talk about that if we have time. So this is a powerful method, but it can be slow. It still relies on Monte Carlo, right? You're still using simulation in order to construct these transfer functions in order to get this piece here so we can do these integrals. There are some people that try to extract these transfer functions from the data directly in order to have less dependence, but in the end, we still rely on Monte Carlo. And there are some assumptions here, right, in order to make this tractable at all. But it's a totally different way to come up with your statistical model, right? And I like it because it starts from the actual expression we think of when we want to write down what is the probability of seeing various things in our data. Okay.
Is this performed inside Interpolate as well? So is it done on background and
If we knew which events were top events, we would be in a better situation. So you make a selection. Say here, these are events. This is a sample that's rich in top, right? And then you apply it to all of those events.
So that expression is not done for signal plus background.
It's done for the events in the data, which are signal plus background, right? Yeah. However, so you raise a good point. This integral assumes that every x is similar, like they have the same number of jets, same number of leptons in order to do this integration. So you can't just do it on every single event you collect. So you have to apply a selection first and say, here are all events that are similar in that way. Maybe that was your question, yeah. But of course, you don't know which events are signal and background. And then you try it on your simulated events and you say, how well does it work? And you can use that to calibrate it. All right, so we have those various approaches. They all have their strengths and their weaknesses, right? So once you have a statistical model, then you can start doing fun stuff with it, like hypothesis testing, right? And statistical inference. Because in the end, you're not interested in the statistical model itself. You're interested in the statistical model because you want to use it to say something about nature, right? We want to say something about these parameters theta so that we can write papers and reveal the secrets of the universe. More often writing papers than revealing secrets of the universe, but eventually. All right. Okay. All right, so hypothesis testing. Okay, so this is our game, right? We want to know standard model or standard model plus X, right? Where some theorist has come up with a way to extend the standard model to solve some aesthetic problem or whatever, some new idea. And we want to ask nature this question. We want to say, nature, which of these two things do you prefer, right? Is it a standard model or standard model plus X? And so there's various cases here, right? There's your decision. And then there's the truth. Right? And so then there's 4 possible outcomes. Right? Okay, so so if it's a standard model and you declare the standard model and you do your experiment, you say, I think the standard model is correct, then you call this a true negative, right? Disappointing, but at least you're not wrong. If there is some new theory of physics that's actually true and you've proposed it and discovered it, awesome. True positive. Few people ever visit this square. I hope that one of you gets to. Right, these are the good situations. If the truth is the standard model and you have declared the discovery of a new particle, right, then this is a false positive, right, also called a type 1 error. Okay, and this is a false negative. Right, this is nature has a new particle in it. You said it doesn't. And there's examples of both of these in the literature, which are sort of hilarious to look at. I mean, there's examples of LEP claiming to discover the top quark, for example, when they just didn't understand their background. Or one of my favorite false negatives is a paper by Leon Lederman in PhysRev D, where he's looking at the mass of muon pairs, and here's 3 GeV, and he has a spectrum that looks like this, and there's like totally obviously a bump in there. And the figure legend, I don't have it here, says, "We observe a smooth spectrum with no obvious resonance features." And you're like, well, there's the upsilon. I mean, there's the charm quark, dude. But whatever. Anyway, it's like I can send you guys the paper. It's pretty hilarious. So there's examples of both of these. Okay. Was it a theorist who fit that curve? Maybe you know more details of the story. I've only heard it third hand. Right, okay, and so how do you make this decision, right? How do you do hypothesis testing? How do you construct an experiment and know when to make a decision, right? Well, in a 1D case, it can be pretty simple, right? Say you construct your experiment, so you measure one thing, a number of somethings. You're curious, are there any blonde physicists, for example? And so you have a background hypothesis, right, that says, well, I will observe no blonde physicists. But, maybe there's some uncertainty there because sometimes you mislabel brown-haired people as blonde. And then there's an expectation for what you would see if there really are blonde physicists, right? Signal plus background versus background only, right? So you have two hypotheses here. And in a one-dimensional case, it's pretty obvious what to do. You can just set a threshold, right? You can say, above this number, I will declare discovery. And below this number, I will claim the null hypothesis, which is that there are no blonde physicists, right? And it's pretty obvious what to do here. You set a threshold, and you can tune this threshold, right? You can tune this threshold to try to balance these two different kinds of errors. Okay, so more arbitrary terminology. The false positive rate we call alpha. The false negative rate we call beta. Okay, there must have been like two different schools of statistics arguing about this terminology. Like call it type 1 or type 2. Call it alpha or beta. Right? Who knows? Typically, so you can tune this, right? You can say, I'm going to tune this threshold so that I maximize my chance of discovery. Maximizing your chance of discovery also maximizes your chance of making a false discovery, right? As you lower your threshold. If you raise your threshold to avoid false discovery, you also potentially miss real discoveries, right? So you can tune this to play off alpha and beta, okay? Now in particle physics, typically what we do is we fix alpha, right? We say we will accept a certain rate of false positives. And we typically fix this to be very small, right? Right? 3 sigma, 5 sigma, whatever. These correspond to the probability of measuring these things. We typically fix alpha to be very, very small, and then try to minimize beta, right? So we want a false rate of false reporting, a small rate of false reporting. Given that, we want to avoid missing something. Particle physics is very conservative. They're very, very afraid of making a discovery and then having to backtrack. I think that's really just a cultural thing. Like, if we lowered alpha to 2 sigma or 1 sigma and said, look, we're going to make these discoveries, some of them are going to be wrong, and everybody knew that, then it wouldn't be such a big deal. But you have to also worry about how do your discoveries play out to people who are not experts in statistics, which is most of the population. And so if we told Congress, yeah, we're going to make discoveries, but about 1 out of every 5 is going to turn out to be baloney, right? That's not necessarily going to play very well. But what it means is that we're very, very hesitant to say anything, and it has all sorts of other strange cultural effects. All right, so we try to do this. In a 1D case, not a big deal. If you fixed alpha, right, alpha is your rate of false positives. So fixing alpha means you know exactly where to draw your threshold. Then you can calculate beta, you're done, right? Very simple in the one-dimensional case. Nothing is ever one-dimensional, of course. And as soon as you go to more than one dimension, you already run into difficulties, right? Say, for example, sorry?
So the step after fix alpha is try to minimize beta. In the one-dimensional case, since alpha would fix that, is there any way to minimize that, or is it just good?
The only way to minimize that is to change the construction of your experiment to move these distributions further away. But given the construction of the experiment and the distributions of these things, fixing alpha determines beta for the one-dimensional case. All right, say you make 2 measurements, right? Okay, you're measuring people's, I don't know, hair color and eye color or something. And so maybe your background lives here, right? And your signal lives here. Okay, how do you draw your decision boundary, right? Well, you can say, I like straight lines, so I'm going to make this box. Right? Okay, well, you can do that, and you can even use that to fix alpha. That's cool. But your friend could say, well, I like straight lines, but I can just draw one straight line. Yeah, that's cool too. And maybe your other friend says, I like curved lines, and this one works even better, right? And so there's an infinite number of ways, number of choices for your decision boundary, right? And so that gets to be an issue, okay? And so here's where we get into statistical theory and interpretation, how to draw these lines, how to make these decisions in multiple dimensions, okay? And we have 2 schools of thought, okay? And the way I like to think about this is that both schools of thought sound totally reasonable. Somebody described them to you, you'd be like, yep, okay, that sounds good. But they're totally inconsistent with each other. They lead to very different ways to make these calculations, which usually give you the same answer. All right, so Bayesians and frequentists, they have different thoughts on what is meant by data and what is meant by parameters and what is meant by probability. Okay? So a Bayesian says, look, your data are fixed. Okay? Your data is your data is your data, right? You did this experiment, you got your data. That's all you really care about. The parameters are unknown, right? So you are trying to measure the mass of the Higgs. You did a bunch of collisions at the LHC. You got a bunch of numbers. That's your data. What you don't know is what the true value of the Higgs mass is, right? And so with the parameter here, for example, is the Higgs mass. That's the thing we don't know. This could have various values. And probability reflects our lack of knowledge. Okay? And so for a Bayesian, it makes total sense to talk about something like, well, here's the probability of various Higgs masses. Right? They say, sure, there's some distribution. We don't know. We think this is the most likely because of our data. These are unlikely, but you know, it could be this, it could be that. Everything I said, I think, sounds totally reasonable, right? Frequentist starts from a different point of view. A frequentist says, look, your parameters are fixed, okay? A Bayesian says, you got your data. It doesn't make any sense to talk about other data you might have gotten, right? Frequentist says, no. The things that are fixed is the parameters. We live in this universe. The Higgs mass has a value, right? It doesn't make sense to talk about other values of the Higgs mass. There is one number. Our data are just one example, right? Sure, you did your experiment, But if you had done it a year later or a moment later, you would have gotten different quantum mechanical fluctuations and all sorts of stuff. You would have gotten a different data set. So the data you got is just one example. They're all controlled by the same value, the Higgs mass, right? It's just one example of many. And so probability for a frequentist says is the long-run frequency, right? It says if you did this same thing 1,000 times, or in the multiverse, how often would this happen, right? That's what a frequentist says probability is trying to capture, is the likelihood that this happens given that you do it multiple times, right? Also sounds totally reasonable. But for a frequentist, it makes no sense to talk about the probability of various values, right? A frequentist says, no, there is some value, right? It's just a number. It doesn't make sense to talk about the various probabilities. What you can talk about is the probability of measuring this or measuring that given this number, okay? So these both sound reasonable, though they're inconsistent. And what it translates to is when you're trying to make statistical statements, Bayesian and frequentists ask different questions. The questions sound similar, and it's very easy to speak loosely and mix them up, but they're actually asking different questions. And that's important because the questions they ask determine how they do the calculation, which determines the answer they get, okay? And in statistics, it's always very, very important at first to say exactly what question am I answering, and say that as specifically as possible, because otherwise you're going to end up off in the weeds and doing something that makes no sense, okay? So a Bayesian, right? Say we're measuring the Higgs mass. A Bayesian says, I want to know the probability that my parameter theta, maybe Higgs mass, maybe something else, is in some range theta 1, theta 2. Okay? Or equivalently, find some range, theta 1, theta 2, such that the probability that theta is in this range is equal to some fixed number, 0.95, for example, right? And this comes about from thinking about the probability distribution, right? You have some parameter, you have some PDF, and it says, just tell me the probability that my true parameter is in this range, or find me edges so that I get a certain probability, right? It comes from thinking about the probability distribution on the parameter theta. A frequentist says there is no such probability distribution. Right? He says what you want to do is you want to ask this question. You say, find me a range calculating procedure so that the true value theta is an element of my range in 95% of experiments. Right? So the frequentist says, this is garbage. He says, I just want you to tell me what to do with my data. So for any given data, I know how to calculate a range, theta 1 and theta 2. And I want that procedure to guarantee that 95% of the time, or this is a tunable number, 68%, 99%, whatever, give me a procedure that I can use to find a range which will include the true value, which is just one number, 95% of the time. Which means 5% of the time it will not include the true value. Right? Also a very reasonable way to phrase it, right? Say, look, I just want a range, and I want the true value to be in there 95% of the time. There's no statement here about the probability of various values. It just says, I want to know that my range includes the true value, a certain fraction of experiments. Okay? So Louis Lyons is fond of saying that Bayesians address the question everyone's interested in using assumptions that nobody believes. Frequentists use impeccable logic to deal with an issue of interest to nobody. Okay? Because I think people like to think about probabilities of various parameters. It's sort of intuitive to them. But as you'll see when we get there, to make these calculations requires making some subjective assumptions that are hard to justify. Whereas this is rock solid and we can do this calculation, but people wonder sometimes, is this really what we want? Is this the question we really want answered? Okay, so how do Bayesians and frequentists do this? Well, one common approach is to try to boil down the multidimensional problem into one dimension, right? We want to be back in this one-dimensional situation where we can just have a threshold, right? And so what we do is we calculate something we call a test statistic. Okay, a test statistic is just a boiling down your high-dimensional data into a scalar, right? Say, whatever procedure you want. Am I already 5 minutes over? Okay. Okay, then let's talk about that next time then. Anyway, test statistic. We'll talk about that next time. Okay. Thank you.